In this video, we discuss learning outcome number 1 of lesson 4.4, which is all about understanding and applying the multiplication counting rule. So here's the rule. It says for a sequence of events in which the first event can occur in n sub 1 ways, and the second event can occur in n sub 2 ways, and the third event can occur in n sub 3 ways, and so on, the total number of possible outcomes is just the product of all of those ways that we just talked about. In order to help you understand this idea, I'd like you to think about maybe going to a dancing lesson. I used to take these dancing lessons. I used to learn how to, I was trying to learn how to salsa. And one of the things that would often happen is that I'd show up at my dance lesson and there were 10 women there and maybe there were 2 or 3 men there. And because the men were learning how to lead and the women were learning how to follow, we only had certain pairings. I mean, sometimes women would practice leading, but all the women were really trying to learn how to follow. So rather than using that example with 2 men or 3 men and then 10 women, I'm just going to use the example of 3 men with 4 women. And I've got that on my piece of paper. So I'll show that to you now. Okay. So here's my example, and here are the names of the 3 men, and here are the names of the 4 women. Now, according to that multiplication counting rule, the number of possible pairings here for dance partners is the number of men that we have times the number of women. So if I'm talking about having 2 men to dance with and there are 10 women, well, there are 20 possible pairings. Or if there are 3 men to dance with and there are 10 women at the salsa lesson, as often happened, there would be 30 possible pairings. Now, I'm using 3 and 4 to make it a little bit easier to write everything down. Okay, so let's say we've got 4 women. Well, and we'll just start with me. If I am one of those 4 women, and we're thinking about all the ways that I could be paired up with someone, and there are 3 men there named Philemon, Dallas, and Elijah, I could dance with Philemon, I could dance with Dallas, and I could dance with Elijah. So at some point during the lesson, they'd probably have me dance with Philemon. And then later we would rotate so we could practice dancing with different partners. And then I would dance with Dallas. And then we would rotate and then I would dance with Elijah. So these 3 possibilities just came from me, but I'm just one of those 4 women. So the other possible pairings come from the other 3 women, Jade, Sarah, and Gigi. So Jade might dance with Philemon or Dallas or Elijah, and there are 3 possible pairings there. Sarah would dance with Philemon, Dallas, or Elijah, so you'd have 3 here. Gigi would dance with Philemon, Dallas, or Elijah, so you'd have 3 here. So you'd have 3 plus 3 plus 3 plus 3, which is the same as 3 times 4. So there are 12 possible pairings, which just came from taking the number of ways we could choose a woman and then the number of ways that we could choose a man, and we multiply those together and we get all the possible pairings. So that's the multiplication rule. That's the idea behind it, and that's where it comes from. We talked about this when we talked about the rationale behind the multiplication rule. It's the same idea, but with the multiplication rule, this number 12 was going in the denominator for the number of possible outcomes. Here we're just counting the outcomes. So we're just focusing on that denominator, which is the same as the number of elements in that sample space. Remember, the sample space is the set of all outcomes. And if we're talking about the procedure being pairing dances or partners up to dance, if you're trying to keep the women in one category and the men in another category, so women can learn to follow and the men can learn to lead, you'd end up with these 12 possible pairings over here. Okay, I hope that it helps you understand the rationale behind this rule. Now let's go back to the PowerPoint. And do an example. So this is an example involving a hacker guessing a passcode. So let's say you have a phone or some other device where you are asked to make a 4-digit passcode, and it's a case-sensitive passcode. It's alphanumeric. So every digit can be any number between 0 and 9. It can be one of those digits. It could be a lowercase letter, A, B, C, D, E, F, G, all the way through Z, or it could be an uppercase letter. So it's case sensitive. So those are the possibilities for a single digit. And now we're talking about a 4-digit passcode And it's okay if you repeat the digits. I wouldn't recommend having a passcode of 1111, but that is one possibility. Okay, so that's the setup. Here's the question. What is the total number of different possible passcodes? And then, assuming that all guesses have the same chance of being correct, what is the probability of someone correctly guessing the correct passcode on the first attempt? I guess I said correct way too often there. I'll have to edit that before I post it online. But you get the idea. Okay, so let's talk about those 62 different possibilities that I mentioned here. You've got 26 letters of the alphabet, lowercase and uppercase. That's 26 times 2, which is 52. And then you want to add those 10 digits 0 through 9. So you've got 10 plus the 26 plus the 26 again, or 10 plus the 52, which gives you 62 different possibilities for each digit. Now, because we are allowing people to choose a second digit that is the same as the first digit, you've got 62 possibilities for the second digit, 62 possibilities for the third, and 62 possibilities for the fourth. So the total number of different possible passcodes is just 62 times 62 times 62 times 62, which is 62 to the fourth, which turns out to be this 14,776,336 passcodes. Now, we're going to make an assumption. We're going to assume that all of those possibilities are equally likely. And that might not actually be true. Well, it isn't actually true, but if we did assume that all possible passcodes were equally likely, the probability of correctly guessing the passcode on the first attempt is 1 out of those 14,776,336 possible passcodes. Now, it turns out that they're not all equally likely. Hackers know human nature is such that we tend to include names in our passwords. We tend to include certain words in our password. We tend to include birthdays, social security numbers, all of those things. So often, rather than guessing somewhat randomly from that 14,776,336, if they guess knowing how humans tend to behave, knowing that some passcodes are more likely than others, 10% of the time or 20% of the time, they're going to be able to guess correctly, or excuse me, 10 to 20% of the time they'll be able to guess correctly by using those names and common names and words and birthdays and social security numbers and just numbers and words and names of people that person who created the passcode actually knows. So you want to be really careful about that. The best passcode that you can have is one that includes both numbers and letters. There are no actual words in it. You've got a bunch of digits, and then in addition to the alphanumeric passcode that I mentioned here in this example, you can also have exclamation points, at signs, the pound sign, the dollar sign, the percentage sign, like all of those are great to include in your passcode so that people can't get into your devices. So that is our first example of the multiplication rule. I will see you in the next video.